So, Part A asks you to use Gauss's law to find the electric field within the insulator, that is, the smaller inner circle. To do this, you need to first find your Gaussian surface. In this case, it would be a Gaussian sphere inside this circle. This would allow for an electric field that is uniform and constant all around that Gaussian surface. Because of this, E can become a constant, and we can easily solve for it. So, with that Gaussian surface, the integral becomes E dA equals Q in over epsilon naught, because E is parallel to dA. Qn, however, will be kind of tough to find. Qn is the charge inside the Gaussian sphere, and this would equal the volume inside the sphere times the volume density of the sphere, which can be found by the total charge over the total volume. So this equals 4 pi little r 4/3 pi little r squared times q over 4 pi little big R, cubed 4/3. Can't remember my volumes. So then a little canceling out goes along. And Qn equals Q little r cubed over big R cubed. Integral of EdA becomes EA, because E is a constant, and integral of dA is A. A is the surface area of your Gaussian sphere, so that equals 4 pi little r squared equals big Q little r cubed over big R cubed epsilon naught. And solving for E gives you Q R over 4 pi big R cubed epsilon naught. And that's your final answer. Part B asks you to find the electric field within this empty area that's past your insulator but before your conductor. This would be easier than part A in that Qn is easier to find. So still integral, let me change that color. Integral E dA equals Qn, which equals big Q over epsilon naught. And again, E, this is because E is parallel to dA, both vectors, by the way. So E again is a constant, so E and the integral of dA is A. A equals Q over epsilon naught. A is again 4 pi little r squared, so E, when solving for E equals Q over 4 pi little r squared epsilon naught. And that's it for part B. Part C asks you for the electric field in the conductor area, which should be here. However, it's a conceptual concept that inside a conductor the electric field equals 0. This is because all of the charge in a conductor goes to the outer edges, and then they balance out on the inside, so E is just equal to 0 inside a conductor. Part D asks for the surface charge density on the inner surface of the conducting shell. to do this, you would need to find the total charge on the inner surface of the conducting shell, which is this area. So, because the electric field in a conductor is zero, if you apply Gauss's law, then the only way for the electric field to be zero in here, so that means this side of the equation equals zero, that must mean that Qin is also equal to zero. So then the charge on the inner surface of the conducting shell must balance out with the charge on the insulator. So that means that the charge equals negative Q, because the insulator's charge is positive Q. So to find the surface charge density, sigma equals the total charge over the total surface area. And this equals negative Q over 4 pi, the radius squared. In this case, the inner surface of the conducting shell is 2r, so 2r squared. And this equals negative Q over 16 pi r squared. And that's your final answer. Part E asks for the surface charge density of the outer surface of the conducting shell. So, since the total charge of the outer conductor, this whole thing, is equal to plus Q, total charge, that must mean that the outer surface of the conducting shell is equal to the total charge minus the charge on the inner surface of the conducting shell, which is equal to negative big Q. So that equals Q plus big Q. And again, to find the surface charge density, sigma, you just need to divide that by the surface area, which is again 4 pi radius squared. In this case it's 3r squared. So sigma equals Q plus big Q over 36 pi r squared. And that's your final answer.